Hello and welcome to my talk on MuonTrap, our new Spectre mitigation strategy designed to restore domain boundaries such as between processes by moving all speculative state into small filter caches at the L0 level. These filter caches are designed not to leak information to the rest of the cache hierarchy and to be cheap and efficient to clear whenever any state may become vulnerable. So first, how do Spectre attacks on caches work? In the example on screen, first an attacker primes the cache with a piece of data of its own. Then, the attacker tricks the victim into bringing secret data into the cache via speculative execution, such as by poisoning the branch predictor or branch target buffer. Finally, the attacker tricks the victim into using that secret data as an index for another memory access. This either will or won't evict the attacker's primed data, allowing the attacker to learn partial information on the secret, who can then repeat the attack until they can learn it in its entirety. This is just one example of such an attack. The fundamental property is that state can be altered speculatively based on a speculatively loaded secret, resulting in a side channel to discover that speculatively loaded secret. These attacks are useful primarily in two scenarios. The first is to allow an attacker to escape from a sandbox region in a processor's address space, such as JavaScript in a browser. The second is in leaking information across process boundaries. We mainly focus on the latter as it's the most applicable to all applications and the only one of these that can't be fixed using process-level isolation, though MuonTrap does offer solutions that can help with the former as well. Okay, so the invariant that we're trying to achieve is that no information that can leak the behavior of speculative execution can leak out into the state of the system, except for in small regions that can be cleared quickly and in a time-invariant manner, whenever the state within might become vulnerable to being read by an attacker. So, we take the traditional cache hierarchy and add in a filter cache at the L0 level to store this speculative state. The idea is that this is a small area close to the core that can buffer the results of any speculative cache accesses. It can be wiped whenever an attacker may be able to read it, such as on a context switch. These properties allow the speculative filter cache to be virtually tagged, unlike most L1 cache designs, and as a result, this L0 filter cache will typically be faster to access than the larger L1. We want to be able to wipe the filter cache quickly whenever its state might become vulnerable, and in a time-invariant way that doesn't leak its contents or how much data is stored within. So, the filter cache is write-through, meaning it's always safe to invalidate data within it, and we store a bit register separate from the SRAM cache and each accessible in parallel, per cache line in the filter cache. This allows us to unconditionally wipe a filter cache contents within a cycle by accessing each of those bits in parallel, and we can do that either on domain switches or under configuration. After any arbitrary misspeculation, those can be wiped to wipe out the entirety of the data in the cache. Now, that means that we can wipe the filter cache whenever any state might become vulnerable, but it doesn't show how we keep the invariant that no state elsewhere in the cache hierarchy can be affected by it. As an example of how things can go wrong, consider the example attack on screen. If the filter cache is inclusive with respect to the L1 cache, then the attacker can prime the L1 cache and cause it to be evicted by a speculative access by the victim in the filter cache. Exclusivity can cause a similar problem. So, the filter cache must be neither inclusive nor exclusive with respect to the rest of the cache hierarchy. It can contain data that the other caches don't have and doesn't need to evict data from those caches. This means it doesn't affect their state. Similarly, data evicted from the filter cache isn't written back to the L1 unless a memory access that brought it in has been committed. In fact, MuonTrap writes through reads into the L1 upon instruction commit. So far, we've only considered filtered caches on the data side, but this isn't the only way that we can leak speculative information through the cache hierarchy. For example, an attacker can instead leak their loaded secret by using it to perform an indirect branch, affecting the instruction cache. So, filter caches are necessary on all cached connections to the memory system, where that structure is written to speculatively, including the instruction cache and TLB. We also have to stop anything else that can indirectly affect the cache hierarchy as a result of accesses in the filter cache while avoiding performance loss. Even if a load into the filter cache can't cause insertions or evictions into the non-speculative cache hierarchy directly, if the hardware prefetcher triggers accesses as a result, then those can be used as a side channel instead. So, to allow prefetching in this scenario without leaking speculative execution, we only allow prefetching based on the committed instruction stream. To do that, while still prefetching into the appropriate level in systems that may have many prefetchers across different levels of the cache hierarchy, when data is brought into the filter cache, it's tagged with the level it was brought in from. If an instruction using that data is committed, then a message to the appropriate prefetcher is sent. For example, a load from the L1 cache will inform the L1 prefetcher but not the L2, as without the filter cache, the L2 prefetcher would also have not been informed of the memory access in the first place if it hit in the L1. The concept of not allowing the state of non-speculative caches via the execution of speculative execution is made more complex as a result of the coherence protocol. Even if the placements of data itself is not affected, if a speculative action causes state in coherence to change, then this can be timed and used as a side channel. In the example on screen, an attacker first loads an object from memory, bringing it in an exclusive state. The victim is then tricked into loading a secret Y, bringing in location X conditionally based on that secret. This will then move the attacker's copy into shared, thus making a subsequent store take longer than it would otherwise. This attack can even be done while the victim is still under speculative execution. Still, we want filter caches to be able to participate in the coherence protocol. This means that loads in the filter cache can be committed without adding a commit time transaction to check that we have the correct coherent value. To do this, MuonTrap uses two invariants. The first is that filter caches can only hold data in shared or invalid states. This means that no filter cache needs to be aware of the data in any other. The second is that a speculative memory access isn't allowed to change the coherent state of a non-speculative cache until the memory access becomes non-speculative. To show how this second condition works while still allowing lots of speculation in the memory system, if a non-speculative cache contains data in an exclusive or modified state, then it is assumed that any filter cache on a direct path closer to the core than the cache in exclusive or modified is able to obtain a copy of the data, and therefore such filter caches can access the data speculatively and any others can't. On the flip side, if a non-speculative access wishes to upgrade to exclusive or modified, then these are the fraction of filter caches that must have their copies invalidated in a time-invariant way. So, for the example on screen, elements in yellow can be accessed, whereas elements in red cannot. Data in exclusive from our L1 cache or the shared L2 cache can be accessed, as can data in shared in the non-private L1 cache, whereas for data in modified or exclusive in the remote L1 cache, we must wait for the load to become non-speculative before that access is allowed to happen. At no point, then, do we discover the contents of the other filter cache. It remains a secret throughout. Once a load has been committed, if we discovered no other copies of the data in non-speculative caches, An asynchronous upgrade can be launched exclusive, which will invalidate any filter caches that could possibly contain shared copies, or rather it will invalidate any shared copies of that data in those filter caches without leaking their contents. Okay, so that was a brief introduction to what MuonTrap protects against and the invariants it maintains. Now, let's look at what MuonTrap does not try to maintain. First, unlike many techniques, MuonTrap by default allows the viewing of speculative state past the point of misspeculation from within a protection domain. This is because, for many applications, the data brought in by misspeculation is useful for subsequent correct execution, and in many cases is not the source of a security vulnerability. MuonTrap can be set to clear filter caches of misspeculation as well for applications that need protection within the process as well as between. And this is made low cost by the efficient invalidation mechanism described earlier, but this is switched off by default. This means that even with misspeculation time invalidation, instructions within the same thread and same protection domain can observe timing information about the speculative accesses currently executing, even if this is not directly possible across domains or from threads on other cores. MuonTrap writes loaded data into the L1 once the data in the filter cache is used by a committed instruction. But a filter cache that is too small can have such data be evicted from the cache before this point. In this case, the load is repeated to bring it into the L1, leaving a small amount of observable contention for a few cycles in this case. Finally, MuonTrap is only designed to target cache and TLB exfiltration mechanisms. We take the view that other structures containing soft state side channels should not be updated with speculative state, whereas this is too vital for the cache system to be prevented, as speculative loads are a critical feature of single-thread performance. Now, onto our simulation setup. We target a high-performance 64-bit ARM core in Gen 5 with the parameters on screen. Particularly of note is that the data filter cache is faster to access than the L1 data cache, which in most out-of-order designs takes multiple cycles to access, since the L1 data cache is physically tagged. This means that a miss in the data filter cache followed by a hit in the L1 takes 3 cycles instead of 2 in the unmodified system, whereas a hit in the L1 instruction cache takes 2 cycles instead of 1. The filter caches are 2 KB or 32 cache lines. We see here that MuonTrap causes 4% typical slowdown on Spec-2006. LBM is sped up significantly because the in-order prefetching mechanism is easier to pick up for this workload than the standard out-of-order prefetcher, whereas other workloads such as Cactus ADM, Leslie 3D and Zeus MP suffer from the cost of the various mitigations, which we will consider in more detail shortly. Still, we see that MuonTrap is significantly faster than the 2 InvisiSpec mechanisms, which are also based on the idea of hiding loads in speculative buffers. Sometimes MuonTrap sees spikes for similar workloads to InvisiSpec Future. This is because both are based on the idea of loads becoming visible only once they reach commit, rather than any earlier, whereas InvisiSpec Spectre releases them while some speculative actions are still occurring. MuonTrap can sometimes show higher overheads, since it covers more than just the data cache hierarchy and handles the prefetch mechanism. Still, this is rare, as it's usually outweighed, for example, by allowing the filter caches to participate in coherence and by not clearing state on misspeculation. If we look at speculative taint tracking, a technique based on limiting speculation on instructions based on loads, then we again see higher overheads, often on workloads that MuonTrap sees little performance loss on. This is because MuonTrap is able to deal with complicated speculative load chains that STT must store on. The same broad pattern is broadly repeated on Parsec, where MuonTrap actually sees a performance improvement of 5% relative to the same system without a secure filter cache. This is because Parsec is particularly amenable to the one-cycle cache access time of the filter cache, whereas for Spec, the filter caches are too small for this effect to kick in, and so performance is harmed by increasing latency to the L1. We set the filter cache to be 2 KB in size for these experiments. We see that at small values where speculative cache lines can be stored concurrently, performance can rapidly lower, as cache lines get evicted before they can be committed, and so accesses to main memory end up being repeated over and over again. Performance continues to increase steadily with larger and larger filter caches because of its faster access time than the L1. Now, let's look a little bit more in detail as to where the overheads of MuonTrap come from. We see in this graph for Spec-2006 that an insecure L0 with the same parameters as the secure filter cache on the data side often causes similar slowdowns to MuonTrap in its total. Still, there are exceptions where, for example, the extra limitations cause further slowdowns, or speculative data not being written back to the L1 if it is not committed cause a significant performance loss. If we look at MuonTrap with clear on misspeculation enabled, we see that the overheads do raise further to 11% on average. This is because the spec applications do make use of misspeculated data in the L1 cache, and so techniques that prevent any observation of misspeculated accesses will fundamentally miss out on performance. For Parsec, we see a slightly different pattern, where a one-cycle filter cache improves performance instead of diminishing it, and so that's why we see a speed up from standard MuonTrap and a less significant slowdown for clearing on misspeculation as a result. Okay, so Spec suffers from slowdown from the L1 cache being a cycle further away in our setup than in the baseline, by virtue of the filter cache being in the way. So, what if we instead allow the filter cache to be accessed in parallel with the L1 cache? We see in this case that the 4% of the yellow bar goes down to 2%. Some workloads do still suffer significant slowdown for the various reasons we've covered already, but this is rare. Most are unaffected to a significant degree, and so if we're willing to accept some further system complexity, we can reduce overheads further and bring about very low overhead domain boundary Spectre resistance. So, that was an introduction to MuonTrap, our filter cache-based technique to clear state in a time-invariant manner whenever it might become vulnerable to leakage, especially in the context of domain crossing such as between processes, including new techniques to avoid leakage from the prefetcher and the coherence protocol. Thank you very much for listening, and if you'd like to know more, please attend and ask questions at the live session at ISCA', or if you can't make that, then please email us. Thanks again, and goodbye.